Okay, let's get started. So last time we started talking about interacting systems, and we were interested in non-ideal behavior when there is an actual interaction potential between things, which is almost everything in life. And in order to talk about that, we introduced a bit of hierarchy. We talked about the joint probability distribution, right? We wrote a very, very general expression, which is, you could think of a joint probability distribution, which is for all n particles in a system, which depends on the coordinates of every atom. And that will be proportional to e to the power minus beta e multiplied by u, which is the n-body potential interaction term, right? How everything talks to everything else, which depends on R1, R2, up to Rn. And then we simplified this. We said, well, let's just look at two particle joint probabilities, R1, R2. How do we look at two particle joint probabilities? That's going to be proportional to this thing, but integrating out everything else apart from R1 and R2, right? So we integrate, and I'm not using vectors because it's a lot of arrows to draw, so we integrate out everything else. And that's how we get the two particle probability distribution, right? But this is still very specific. This is saying particle number 1 at R1, particle number 2 at R2. So from this, we said, well, we don't care whether 1 is at R1 and 2 is at R2 because particles kind of look the same if you have too many of them. So let's look at rho 2 of R1, R2, which is the probability of finding any two particles at R1 and R2. And that thing was not proportional. That was actually n multiplied by n minus 1 multiplied by P2 of R1, R2, right? So this is how we introduced the reduced distribution function. We looked at the reduced distribution function for one particle, and we said if it is a uniform isotropic system, then even though you have interactions in the system, even when you have interactions in the system, this is going to be equal to the density. Well, you're not in Zoom. Messing with me, man. So this is going to be n by v. And this is important that this derivation held true even in presence of interactions. Then we went to second order, and we are not really going to talk about third order. Rho 2 of R1, R2 was equal to rho square for uniform isotropic, which is assumed even here for this one, and no interactions, right? If it is purely ideal, then rho 2 is equal to rho squared, and that was nice. Then we said, well, there are going to be interactions, so it's going to be different from rho squared. What is the thing that, how different is it? That is our G, right? And then instead of looking at R1 and R2, we said, let's just think of terms where only pair interactions matter, so we can just look at the relative distance. So that's, those who came late, you didn't miss much. I'm just recapping. So that's what led us to introduce that if we are just interested in rho 2 of R, so you can imagine that R1 is equal to 0 and R2 is equal to R. So this sounds like profound. Oh, we moved the origin. No, all we are saying is that the system is translationally invariant. It doesn't matter where you are. It's just the relative things that matter. So R1 is equal to 0, R2 is equal to R. And this thing becomes rho square, density square multiplied by G of R. So G of R captures how much deviation from ideality do I have? It captures the interactions in the system. We looked at G of R plots, right? We sketched it and we looked at rho G of R is conditional probability of finding some particle, and we are not labeling the particles here, some particle at distance R from another particle. So if the origin thing confuses you, all you are saying is, if you know there is one particle here, what is the probability that you will find some other particle at distance R? Some of you got confused about how it integrates out and how it diverges and things like that. So in the next homework, in the final homework, there will be a problem where you will see how you really have to multiply it by 4 pi r square in order to do the math correctly. So we showed this, and then I mentioned that G of R, if you Fourier transform it, then it becomes S of K. And this is known as structure factor. S of K can be measured using diffraction and variety of scattering things. It's easy to measure S of K. And so if you take the inverse Fourier transform of S of K, you get back G of R. So G of R can directly be measured from experiments. What we are going to do now is to really show you the power of the physics that G of R captures. Okay, so we will work through it. Chandler does it in the book. And I'm going to give you more intuition as to why it actually makes sense. So Patrick Kelly seems to insist that Chandler's book is worse than Tuckerman's book and other. One of the, over years of keeping Chandler's book, one of the best advantages of that book is it's very skinny, right? You can go wherever, and you can. When I was a postdoc in Columbia University in New York, I would just carry it in the metro with me. You could just read it on the train, you know. Try carrying Tuckerman's book. You can carry a Kindle, but then what's the fun? Okay, so today I'm going to show you that G of R. Go ahead.
So in the conditional density thing that we proved, we had a step where towards the end we said that capital P, which is not the conditional, not the reduced probability density at R is equal to P of 1 at 0.
Yeah.
It's fine when you're doing that for the reduced density because you're not tagging the particle specifically. So you can say your system is translationally invariant or rotationally invariant, doesn't matter. It's an invariant system if it's uniform.
Yeah.
But for the conditional density, we defined it as having a specific particle at R or a
it's a good point. But we are still saying it's specific, but they are all the same. That's the point. So even though it's specific, even though Vedanta is different from Swiman, is different from Kinjal, Kinjal is there. But the probability of finding Vedanta anywhere is the same as the probability of finding Kinjal anywhere, right? So the mathematical function that you use for them, they are the same in the uniform isotropic system. That's a good point. That makes sense? Think about it again. So what I want to do next is to show you something which I think is quite interesting, is really physical information that you can get out of G of R. In order to do this, Chandler just gets into the math and we will do the math. But yeah, go ahead, Alex.
S of K, structural factor at 0 temperature and without any defects. It would be set of delta functions.
Yeah.
And would it be related to reciprocal lattice?
It is all in reciprocal lattice. K is known as the reciprocal lattice. So you're from Russia originally, right? There is a famous material scientist whose name is also the same as of a famous composer, Khachaturian, right? You know this name, right? He was a musical composer. Khachaturian was also a material scientist, and he has some very nice books on the reciprocal lattice and structure factor information, which people in biology never read because it's like hardcore metallurgy, but you can go and find his papers and you'll enjoy them. So he did a lot of work on this like 50 years ago. I think actually his first name was also Arman Khachaturian, which is also the first name of the composer. So it's really confusing. Okay. So what I'm going to do next is to ask you a few questions and try to give you intuition into what we are going to do next. So let's get started with a box. And in this box, once again, we are going to put Swiman and Kinjal. Is that okay with you, Swiman? Is that okay with you, Kinjal?
Yeah.
Okay. So we have Swiman and we have Kinjal, and they're ideal. They don't know what's going on. They are just bouncing around doing elastic collisions. At the same time, and if they are really ideal, their dimensions have to be point-like, right? So you have to imagine they're point-like. So the question I have for you now is, so what is this? This is Swiman and this is Kinjal. Now, on top of these, in addition to these two, let's add a bunch of other particles, okay? Which are also bouncing around. Now my question for you is, if I want to study the force experience between Swiman and Kinjal. For now, imagine there is nothing else in the system, okay? Only Swiman and Kinjal are in the box, okay? And it's a big, big box. They are moving around. I want you to answer the following question. What is the force as a function of R if both particles are ideal? How would this force look like? Since Suimin is in the box, I think she should be interested in this. Suimin, what do you think? So it's ideal particle, right? So when you are over here, what force are you experiencing? Yeah, zero. It just doesn't matter. You can go left, you can go right. When you are over here, what force are you experiencing? Zero, right? There is no force. What happens to the force at R tends to zero? You hate it. You tell Kinjal, go away with infinite force, right? So it blows up over here. And it looks like this if particles are ideal. Okay. Now let's imagine that the particles are spheres of radius R. So sorry, of radius A. Okay, so the same thing, but now we are putting a radius A, the same radius for Kinjal, same. So we are doing the spherical cow approximation. Okay, both of them are spherical cows. This is physics, we can do that. So now, Kinjal, what do you think the force will be? If the separation between, so both of you are now spherical particles of radius A. So when radius was, and the question is for Kinjal, Alex, not for you. Not for you. So Kinjal, tell me.
So if the radius is less than A, the force will be
Less than A, are you, we are talking about R, right? If R is A or 2A.
yeah,
If R is less than 2A, the force will be infinite, right? If R is more than 2A, they are again oblivious. They don't talk to each other. So now it will kind of look similar, but at R is equal to 2A, it drops to 0. And before R is equal to 2A, it's infinity. Okay. Alex is going to ask what happens at R is equal to 2A. So it's a discontinuity. We don't care. Okay. It's fine. So it's a step function which goes up to infinity. So we can see this because we understand what is the nature of interaction, right? So now if there is more complicated interaction between the particles, the force versus R will not look so simple, right? It will look very, very complicated. There will be some behavior that's going on. And another complication will come in that if you add some sort of interaction between the systems, maybe it's a harmonic spring, maybe it is something else. On top of that, you have interactions between everything else also, right? Everything else is connected to everything else. So now when you talk about the force as a function of R between two particles, you really have to account for what about the other particles, right? So when these two are interacting at a certain distance with a separation R, and if all the other particles are out in this corner of the box, that force will be very different from if these particles are sitting in the middle of these two, right? So you really have to account for what's going on elsewhere. So
this is for non-ideal.
yeah. Now we are in interacting systems, but you can take the limit and you will get everything that applies to ideal. The same things apply. So what we are really interested in is looking at the n particle potential energy, right? And if I have two particles, say 1 and 2, I'm just labeling them for the purpose here. They are really distinguishable. And a bunch of other particles, 3, 4, 5, 6. They could be spherical particles. They could be point-like. I don't care. And I have some distance r between them, right? I want to calculate the force experienced by particle 2 as a function of R. How would I get this force from this potential energy? Gradient, right? Force comes from potential energy always by differentiating. But what exactly do I need to differentiate here?
With respect to the coordinate of 1.
With respect to coordinate of 1, right? So if I want the force experienced by particle 1, that's going to be minus d by d r1 u of rn. And if you really want to be careful here, it's a gradient, right? It's a vector. So you have to take the gradient of this thing and, so it's, and then look at the component. So this d by d r1 is supposed to signify that it's a gradient. Okay. Stay with me carefully. When you do this and you get a function, right? Let's call this function as f of r. Well, that's my question for you. When you differentiate u of rn, where rn is a shortcut that I'm using to denote the very high dimensional vector r1, r2, up to small r subscript n. Okay, so r subscript 1 denotes x1, y1, z1 for particle 1. R subscript 2 denotes x2, y2, z2 for particle 2. But R superscript n denotes a 3n dimensional vector. Okay, it controls everything. So if I differentiate u of R superscript n with respect to d of R subscript 1, I will get a function, right? What will this function depend on? How about the others? No, why? They're still going to hang there. We have not, variables disappear when you integrate them out, right? Variables don't disappear when you differentiate things. If you have, let's take an example. If you have a function x squared y z squared plus y z x, and you differentiate this function with respect to x, does this stop being a function of y and z? It still depends on y and z, right? If you were to integrate, still depends on y and z. Of course, it could be possible that you have a linear function, x plus y plus z, then the dependence on y and z will go away, right? Normally, the dependence on variable goes away, like happened in this probability when we integrated things out, right? But we are not integrating, we are differentiating. So this function will depend on R1, R2, R3, everything else. Intuitively, what it means that if you're talking about the force experience between two particles, it's going to depend on the environment also, right? So let's leave Suimin alone now. But stick with Kinjal. If you're talking about the force between Kinjal and me, that's going to depend on whether we are having this interaction in this room or whether we are having an interaction in a party, something like that, right? What's going on in the environment, that is captured through these other variables, right? So this is not just a function of R1 and R2, it's a function of everything else. But we might be interested in studying the force between two particles, averaging out everything else. So on an average, what is the force experience between two particles, okay? And in order, before we go ahead, I want to simplify it even further. I want to talk about force not experienced by particle 1, but the force experienced between particles 1 and 2. If you have a radial system where you have only radial interactions going on, then Newton's third law kind of applies, right? Every force has an equal and opposite reaction. So now we are going to think about force experienced between particles 1 and 2. This will depend on R. We are talking about an isotropic system, okay? There is no angular dependence. So it depends only on R. And now this is going to be d by dr of u rn, where R really denotes R2 minus R1, the modulus of this thing, okay? That's what we are looking at. And furthermore, I am interested, force is not derivative of, yeah, go ahead, Sophia.
So when you say R1, R2, is that like, is R1 the distance between 1 and 2? R2?
No, R1 is the coordinate. So I have a system, X, Y, Z, and R1 is where particle 1 sits. R1 is always a vector. So that's why if I used these should all be vectors, but it's too hard to keep drawing arrows. In textbook, you just make it boldface and it works. So that's why small r is the distance between R2 and R1. So if I differentiate this complicated n-body potential with respect to dr, for a spherical symmetric system, if I multiply it by minus, this is telling me the force between two particles, right? But once again, this thing is also going to depend on R3, R4, R5, R6, everything else. Now, I can take an average, an ensemble average over everything else, over R3, R4, R5, R6, then this thing becomes suddenly very interesting. This is now the force between, so we are going to take thermodynamic average over all other particles. So Kinjal and I are interested in figuring out the force between Kinjal and me, but this will depend on what everyone else is doing. If Alex comes and sits in the middle of us, then the difference, it will be different. So imagine Alex is just oscillating around, you are all oscillating around, and I want to average over all possible things that all of you could do. So it's a very, very complicated average, but I could do this. In experiments, it's actually quite easy. In experiments, you will just focus on your two particles and study, right? How they are, you could just study them. But an experiment naturally gives you the averaging over environment, right? If you're observing it long enough, it happens naturally. Simulations, it's a bit harder. So this is the thermodynamic average over all other particles. And it has a name. This thing is called the, well, should I say this is the name? Yeah, I won't give it a name yet. So this is the average that we are interested in calculating. And turns out this thing is deeply connected to G of R. This thing will turn out to be KT multiplied by D by dr of log of G of R. So log of G of R acts like a potential energy. Okay, so this is very abstract, what I wrote over here, and we are going to prove this. Let me give you some more intuition into this, going back to how we drew this force, and then it will make sense as to why this is true. So let's do that. And if this equation confuses you, don't worry. We are going to come back and derive it and work through it. So let's go back to our point particles. Okay, for point particles, anyone remembers how does G of R look? Ideal gas made of point particles. What do you think, Abhinav? It's constant 1, right? Because as R tends to infinity, it goes to 1 everything. So for point particles, it is constant 1 everywhere, right? Ideal gas made of point particles. A couple of pages ago, we drew the force between point particles that Swayman helped us draw. F of R versus R, right? And how did that look like? That was infinite at R is equal to 0. And then it went to 0. Do you see a connection between the top plot and the bottom plot? The bottom plot is the slope of the top plot, right? If you think about what is the change happening over here? 0. What is the change happening over here? 0. Anywhere apart from R is equal to 0, the change in G of R is 0, right? At R right equal to 0, we are in the land that Alex lives and thrives in, the land of discontinuity, where there is a sharp change, right? Even for a point particle, if you went R is equal to 0 exactly, what happens to G of R? There is a discontinuity, right? That's where is it 0 or is it infinite? It's 0, right? The conditional probability of finding another particle, if you already know you are there, that goes to 0. So I was wrong in this one. So if you think about how quickly did G of R change at R is equal to 0, it changed infinitely fast, right? How quickly did log of G of R change? That also changed infinitely fast, right? So you can see intuitively why this is capturing the behavior that I drew over there. It's not clear from this intuitive argument as to why is f of r not just derivative of g of r. Why did we have to take log of g of r? That will become clear through the math. Does it make sense to everyone?
Can you just go over what happens at the discontinuity?
So at r is equal to 0, what is the value of g of r? No. If you are sitting there, what is the conditional probability of finding me sitting on top of your head? You really think it's 1? There you go. And if you were point particles, I mean, I can do the experiment if you want. You won't like it. So, but as soon as you go to slightly larger r, the probability becomes 1 for an ideal gas, right? So the point I'm making here is that, let me write it down. So g of r is equal to 0 at r is equal to 0. G of r is equal to 1 at r is equal to epsilon for all epsilon more than 0. Okay, that's the argument. So this is if you take the derivative of the log of this. So now you might be like, well, log of g is 0. What are we doing? You have to think about L'Hopital rule and things like that. But trying to give you intuition that a force is related to how quickly g of r is changing. Let's go one step further. This was ideal gas. How can we make ideal gas? So this was for ideal gas. Now let's go to not a full van der Waals gas, because van der Waals gas has more complicated things, but let's make the ideal gas have particles of a finite size. I should write page numbers. So page number 2, page number 3, page number 4, page number 5. Now let's make the same plot. Top and bottom, g of r versus r for a gas of particles made up of finite radius a. How does this g of r look? At r tends to infinity, of course, we know this is also going to be 1, right? How about r tends to 0? 0, right? In the middle, Alex, how will it look like?
Depends on the radius.
Yeah, so tell me. So it's going to be 0 until 2a, right? Until 2a it is 0, and then it jumps up to 1, right? This is the g of r for a hard sphere gas. So this is hard sphere gas. How about the force? So let's think about the force now. F of r versus r. If the distance between the two hard sphere, their center of mass is more than 2a, then there is no force, right? So we know once again that it goes to 0 if r is more than 2a. How about r less than 2a?
Whatever we want it to be, because we'll never get beyond closer than 2a.
Yeah. The probability of the system, it is just not going to exist, right? The hard sphere stops it. But exactly r is equal to 2a, what will you have for the force? It will be delta function, right? It impacts. I mean, if you have to be really careful, it's just asymmetric delta function. It really does not make any sense for r less than 2a, but I'm just going to draw a delta function. So once again, you're seeing what did we have over here? This was like a step function, right? The Heaviside step function. And this is a Dirac delta function. And I'm being sloppy in how symmetric it is. Does anyone know how do you get a delta function from a step function? By differentiating. So again, you're seeing this dependence, right? That the force has something to do with differentiating the g of r.
But g of r is not the conditional probability density. Rho times g of r is the conditional.
Yeah, we go to some unit where rho is 1. We are physicists. Units we change anytime, except when it's in your homework, and I deduct your points.
Is there any meaning to f of r when r is less than 2a?
No.
All right.
This is imagination. It does not really mean anything. Okay, for r less than 2a, because the particles cannot just get more than that. The probability of finding system there is 0. It just doesn't matter. So let's go to one more example, and then I will get to the math, which we will do today. So we did ideal gas, point particles, we did hard sphere. Let's go to crystals. For crystals, G of R versus R, again, as R tends to infinity, it's going to get to 1, right? But in the, and R tends to 0, it's going to be 0 because you cannot have any other particle. And the reason why G of R goes to 0 at R equal to 0, that lies in the conditional probability, right? Because you know one particle is already there. So the probability of having any other particle right there is you cannot have two atoms occupying the same site, right? So in crystals, it's going to look like a delta function. Then it could go to 0, but due to thermal fluctuations and things like that and defects, maybe it hovers to some value which is slightly larger than 0, then it goes up and something like this, and something like this. This is it will have more oscillations before it goes further. So this corresponds to the first nearest neighbor. This corresponds to second nearest neighbor. This corresponds to third nearest neighbor. If it was a perfect crystal at 0 temperature with no thermal, no defects, then these would be exact delta functions. This is a good point for me to tell you one of my favorite quotations from when I was doing material science, which is defects make men and materials interesting. I mean, this was written in a generation when women clearly did not do science. I'm sorry, maybe 100 years ago. So you can, but I like this quote a lot. Most of the things that happen in science are interesting due to the presence of defects. Otherwise, it's all just boring, So, okay, so we have this. Now so this is a crystal. Now let's calculate the F of R intuitively, how it will look for this thing. F of R versus R. And I will draw these lines like this. Once again, as you go, R tends to infinity, it will go to 0, right? There is no correlation, nothing. It just doesn't matter. It has to go to 0 at some rate. How about in the beginning? And don't try to get it from the G of R plot. Think intuitively. What will happen? It will be again kind of similar. You can hover where you are. You can keep undergoing your oscillations, right? But it will again kind of look like something like this, right?
Doesn't it depend on how, considering what the potential interaction between the, if they have a harmonic potential, you have a difference.
Sure, and that will decide how these curves, the shape changes and everything. And I will show you that's why we do the math. But physically, it should look something like this, right? It should have a peak when you get to the first nearest neighbor. That's when the force will become very high, right? It's like, don't come close to me. In the middle, whether it goes to 0 or not, that will, yeah, absolutely correct. That will delicately depend on the nature of the interaction. But this feature that you have peaks corresponding to the nearest neighbor distance will be preserved. So you can imagine why, as scientists, you might be interested in calculating this force between two particles in a very, very complicated n-body system. And you can also realize why this is so hard to get. But if you could calculate G of R, if you could calculate S of K through scattering, take its Fourier transform, in your Fourier transform, get G of R, and you could derive a relation that tells you how to get the force from G of R, then G of R is really powerful, right? Because this thing could come from scattering. And as Vedant mentioned, in order to really see what's happening in the middle and distances like that, you have to understand what is the nature of interaction. But when you do this scattering experiment, you don't need to understand anything about the nature of interaction. My friends who used to do scattering at Oak Ridge National Lab, for them, it was basically like a long party. They would go there, set up their sample, have a great time and come back with their G of S of K versus K curve. And from that, of course, sample preparation is very hard. It will take a lot of time, but the experiment itself, they did not have to assume any model, right? It could be absolutely anything. And from that S of K, they would get G of R. From G of R, they would get F of R. And that's exactly when they would start to think about whether the interaction is harmonic, it's anharmonic, what's going on, all those things. So it's.
But assuming you had no thermal fluctuation in your system, wouldn't the force just be 0 until you reach the internal?
Sure.
So it should just be straight lines.
Yeah, but no thermal fluctuation. We are talking about interstellar domain.
No, but I'm
There will always be thermal fluctuation, right?
just this plot.
Yeah, sure, sure. So, okay, so hopefully I gave you intuition, or maybe I confused you more, but it is what it is. Let's go from here. So the result I'm going to prove next is going to make all of this rigorous. And as I wrote it earlier, we are going to calculate, we have the n-body potential function, which is super complicated. We don't know what it is. And we are going to differentiate it with respect to small r, which is small r is equal to r1 minus r2, this distance. We will take a minus sign and we will average it over. We will keep r1 and we will average over r3, r4, r5, everything else. So this is really a very complicated 3n dimensional vector. So this is terrible. Even if you knew the formula for u, it would still be terrible, right? Because in order to do this, you would have to, it will be such a complicated integral, right? It's a very, very high dimensional complicated integral. So it's very hard to do, but it turns out that this thing is equal to k t d by dr of log of g of r. You saw intuitively why that should be related to the derivative of g of r, and now I'm going to show you why it's actually why this formula holds true. So in other words, yeah, so this is the second physical importance of g of r, right? Rho g of r was the conditional probability of saying something, and now if you differentiate g of r, you can actually talk about the average force between two particles. Yeah, go ahead.
Previous slide.
Uh-huh.
If we differentiate g of r, wouldn't the force be negative on the downslope after between, for example, after 1m?
Uh-huh. That's correct. That's correct. So the plot that I drew has an error. It cannot just go to 0. It has to flip signs, right? So you're absolutely correct. So this thing, so tell me, Alex, how will it look like? It will be, it's going to be something complicated, right? It will
Yes,
flip.
it should be 0 at 1m, 2m, and so on.
Okay, you'll all draw it. Great, thank you. And we can thanks Alex. My point about the peak location applies, and in the middle you will have oscillations, because for a certain distance it will be like, oh, you can come further, you can come further, you can come further, and beyond a certain distance, like go away, go away, go away, right? So that type. So you have to think a bit carefully. So this is the relation we want to prove. Any questions? Okay. So now I'm going to follow Chandler's proof to the dot. So it's going to be mathematically a bit messy, but not too bad. You have seen worse. You have been through worse. So in order to do this, what I'm going to do, just to give you a little bit of visualization, I have my box. In this box, I have lots and lots of particles, which are all talking to each other. Okay, I'm going to focus on two specific particles. One is happy, one is ambivalent. And I want to understand the force being experienced between these two particles as a function of R, averaging over the thermal motion of everything else. So you have to really simulate everything else for the age of the universe. Okay, that's what we want to study. So in order to do this, we want now the force between two particles averaging over everything else. So in order to do this, I will start with row 2. Chandler does it for a even more generic setup. He starts with row n. I'm just putting n is equal to 2 and working through the math. So if you look at Chandler, you'll be like, wait, where is it 2? He does it for n, but we don't care about that. We are just going to look at two particles. So we are interested in the reduced distribution function R1, R2, and we will simplify things later. How is this connected to the density? This is rho square multiplied by G2 of R1, R2, correct? This was the definition of G. This means that G2 of R1, R2 is equal to rho superscript 2 of R1, R2 multiplied by 1 over rho square, right? What is rho? Rho is n by v, right? Number of particles in a given volume, kilogram per meter cube. Yeah, so that's rho. Let's call this equation 1. Let's call this equation 2. Let's go to next page. So equation 1 and 2 imply that G2 of R1, R2 is going to be, so the reason I'm sticking with R1, R2 now is because I want to derive something where it's not just isotropic. You know, I will derive a framework which is actually applicable even to non-isotropic systems, and then we'll see how the relation comes out.
Is G defined only for two particles? Or can you
G2 is defined for two particles. If you read Chandler, he does with Gn, which can be defined for n particles.
So small sidetrack, but then for a k particle system or whatever it is, generally you have rho par k. So then what would your conditional probability density be? Would it scale as rho par k minus 1 g of r?
Yeah. So G2 R1 R2, I think so. I have to think more. G2 R1 R2 is going to be v to the power 2 by n to the power 2 multiplied by rho 2 of R1 R2, right? All I have done here is to put in the value of rho over here, right? Rho is n over v, so it becomes v square by n square. Okay. Let's do one more thing. Now write it down as v square by n square. What is the connection between rho 2 and P2? Anyone remembers? N multiplied by n minus 1 multiplied by P2 of R1, R2, right? This was how we had defined rho 2. Okay. Therefore, this thing is equal to v square by n square one moment. I'm going to do something which is purely so that when you look at your Chandler's book, you won't get confused. Okay, so I don't have to do this step, but I'm going to do it anyway. N multiplied by n minus 1 can be written as, do I need to do that? No, I'm not going to do that. Yeah, Patrick doesn't like Chandler's book, I will remember. So I will also skip Chandler's notation. It's unnecessarily complicated because we have to come down to two particles. We will stick with this. Okay, let's just stick with this. So n multiplied by n minus 1 multiplied by P2. Now let's think about what is P2. How do we get P2 from the Boltzmann probability? Anyone remembers? We wrote it on the first page. That's your hint.
E bar minus whatever u of
E to the power minus beta, the full n body potential, right? U, which depends on Rn, on everything. But I have to integrate a few things out. what should I integrate out?
All of them except R1.
Exactly. So dr3, dr4, dot, dot, dot. Is that the probability? Probability needs to be normalized also, right? So I have to divide by the n particle partition function Qn.
Why do we assume that the probability is always going to be Boltzmann-like?
Oh, we are working in canonical ensemble.
Why did we?
We derived it.
No, no,
Remember Taylor's
we-
theory?
Not that the derivation. Why did we explicitly assume we're working in a canonical
I guess I forgot to mention it's canonical ensemble. Yeah, even Chandler forgets to mention if you think about it. Okay, we are thinking about n particles in a box at a volume V at a temperature T. No pressure fluctuations, okay? Yeah, you're right. So assuming, honestly, until this point, we did not assume canonical, right? If you think about till this line, that's why I did not mention. Now we are assuming. So I don't have to feel that bad about myself. Assuming canonical ensemble. Okay, let's go one step further and so this is G2 of R1, R2. Let's call this as equation 3. Now let's write down Qn also. What is Qn? So G2 of R1, R2 is going to be V square n minus 1 by n square, and all this stuff is going to not matter later. So we'll just keep it in one line, multiplied by integral e to the power minus beta u of Rn dr3, dr4, dr5. What is Qn? Arka, what do you think? Minus beta u. And what should I integrate over? Everything. It's the full particle partition function, right? Partition function is one of those things that looks almost useless because everything is integrated out, yet it captures so much information, right? So the only difference, so keep in mind, the only difference between the top and the bottom is where you start integrating. In the top one, you start integrating at R3, you keep R1 and R2. In the bottom one, you integrate everything out. Okay, if this gets confusing, you know, it's simple, but it's confusing. So please stop me. There's no shame in stopping me. Okay. So this is G. G is a probability. In math, there is a problem with probability, right? Probabilities can become very small every once in a while, right? So when people think about the stock market crash, right? It's like, oh, today I made money, tomorrow I made money, next day I made money, or a Thanksgiving turkey, right? Today it stayed alive, tomorrow it stayed alive, next day it stayed alive. So the probability of the Thanksgiving turkey getting killed is actually very, very small, right? So the point I'm trying to make here is, once again, probabilities can become really, really small, right? Before you know it, they can look like 10 to the power minus 16. If you're dealing with very small numbers, your computer code can blow up, right? It will be like, I don't know what's going on. So when you have very small numbers, a better way of dealing with it is to look at the log of the small number, right? So if you're, instead of looking at 10 to the power minus 16, if you look at log of 10 to the power minus 16, then it's a well-behaved minus 16, right? So what we are going to do next is to switch our, and I'll come to you just in a moment, Sarah. We are going to switch. We are going to look at G2 of R1, R2 on a log scale. Okay, so those of you who do molecular dynamics simulations like Swimin and others, we don't look at probabilities, we look at free energy, right? Which is log of the probability. So anytime you have a histogram, look at the log of the histogram instead of looking at the histogram. Yeah, go ahead, Jared.
For Qn, do we need that? Do we need a factor of n factorial here at all?
Sure. No, you are absolutely correct. So they should have. You're absolutely correct. But the nice thing is it's all going to go over here, right?
Yeah.
So what I'm going to do next, so it will actually have h to the power 3n and n factorial. Let's call it capital G, which is acronym for garbage. Yeah, it's okay. You know, we don't care about that right now. If you were interested in n as a function of n, it won't matter for now. Okay, so we will just call it capital. Let's make it more sophisticated. We will call it garbage with like a cut over here, right? So look, fancy garbage.
Actually, it would, right?
Huh?
When if you're going to start calculating.
It does not depend on position. So we are interested in how things depend on position, right? R1, R2, R3, all the functions are gone out. So for our function purpose, it's not going to matter. For some other purpose, it matters. For example, Gibbs paradox tells you, if you ignore this thing, your entropy will be non-extensive. So it's not always garbage, it's special garbage, okay? Don't write that in my teaching evaluation. This course was special garbage. No, please don't. What have I done? Okay, so we are going to introduce G2 of R1, R2 on a log scale. So in order to do that, we are going to look at log of G2 of R1, R2. And not just that, we want this to look like an energy. What is the dimension of log of something? No dimension, it's dimensionless. What is the dimension of energy? Well, KT, right? So anytime you have something and you want to make it look like dimension of energy, what do? You multiply it with a KT. If you're a physicist, you don't multiply with a KT, you multiply it with a 1 over beta, right? So that's what we are going to do over here. We are going to multiply it with a 1 over beta and give it a minus sign. Okay, this looks like, wow, what have we done? No, this is just to deal with conditional probability. As you saw in this plot, most of the time it's going to hover around 0. That's going to be a number like 10 to the power minus 18. Do you really want to deal with that? You will, if you code it up or even in your instrument. I mean, this is like when in UK, when in United Kingdom, when COVID started, their forecast was totally off because they were using Excel spreadsheet where they could fit only 6 decimal places. And no, this actually led to policy error because they were using Excel spreadsheet. The number stopped at 6 decimal places or something, and they had huge policy errors. And then they realized, oh, we should have used maybe log of probabilities and maybe used Python instead of Excel spreadsheet.
I think I've heard of the basic version of Excel or something.
Oh yeah. You don't even need old version of Excel for that.
They're British, they can't afford it.
Here's another joke. People really found out what's really going on in ChatGPT. It's Mr. Clippy. Remember that one from PowerPoint? Mr. Clippy here to help you. Okay, let's come back. So we are going to look at log of G2 multiplied with a minus 1 over beta, and we will give it a name. We will call it W. Okay. So this will be W2 of R1 comma R2. And we have just defined W as this way. Okay, so this is equation 4. And later W will have a name. W will be known as potential of mean force, which is PMF, which is fundamental to molecular simulations everywhere. So we will come to that. So just keep this in mind that W is minus 1 over beta log G2 of G2 as a function of R1 and R2. Okay, so so what we want is to get W. In order to get W, I have to take log of, actually, let's call this equation 5, and this one is equation 4. So I have to take log of everything else, everything over there, right? So let me write down equation 4 once again on the next page. So equation 4 is going to be G2 of R1 comma R2 is fancy garbage multiplied by integral of e to the power minus beta u of Rn dr3 dr4 divided by integral of e to the power minus beta u of Rn dr1 dr2 ... Okay, and we take its log. So log of G2 is going to be log of fancy garbage plus log of the top integral e to the power minus beta u of Rn dr3 dr4 ... minus log of bottom integral e to the power minus beta u of Rn dr1 dr2 ... Okay. And what is the relation between log of G2 and W? Minus beta multiplied by W, right? So this thing is minus beta multiplied by W2, right? This is how we defined our W2. So minus beta multiplied by W2 is equal to log of fancy garbage plus log of something minus log of something. Okay. Now, what I'm going to do is to differentiate W2, differentiate this thing, both sides, with respect to the coordinates of particle 1. Okay. So I'm going to do minus beta gradient with respect to 1 of W2. Okay. Why did I put gradient? Because it's a vector, right? We are trying to look at a vector. So I'm taking a gradient. That's why I put a gradient. If I do the thing, what is the gradient of log of fancy garbage with respect to R1? Does fancy garbage depend on R1? So this gives us 0. How about the third term? Does this depend on R1? Who thinks it depends on R1? The log of the integral. Fahad. Why not? It's integrated out, right? R1 is gone. So if you differentiate this with respect to R1, you again get a 0. The only thing that depends on R1 is this thing over here. Okay. So let's differentiate this one with respect to R1. That's going to give us the log of something. When you differentiate it, what happens? The whole thing goes in the denominator, right? So you will get denominator e to the power minus beta u of Rn dr3 dr4 ... numerator. Now the numerator becomes interesting. We have to go inside the integral and differentiate it with respect to R1, right? So how is that going to look? That's going to look like, first we have an exponential. What is the derivative of an exponential? An exponential, right? We all, we love it for that reason. So that's going to be simply e to the power minus beta u of Rn. Now we have to differentiate u of Rn with respect to particle 1. So that's going to give us minus beta gradient with respect to 1 of u of Rn multiplied by dr3, dr4, dr5, something like that. Okay, just product, no, chain. Which rule is it? Chain rule inside the integral. Okay, and if this step is done exactly the same way in Chandler, it's a bit more complicated because he's not looking at 2, he's looking at k particles at the same time. Okay, let's simplify this integral. That's going to look like numerator, and I'm just going to rewrite it in a slightly different way. I can cancel out minus beta and minus beta from both sides, right? This beta and this beta gets cancelled. Okay, there it's both sides. So what do I get now? I get e to the power minus beta u of Rn multiplied by minus of gradient with respect to position of particle 1 of the full n particle potential energy integrated out dr3, dr4, dr5 ... And in the bottom we have again the same exponential, but this term is missing. The derivatives are the same. Sorry, the differentials are the same. It goes on till everything. What does this look like? Is this an expectation value? It's a very special type of expectation value, right? Previously in statistical mechanics, when we had to compute.
I'm sure you have the same differentials in denominator.
Sure.
Because like in the top row, in the denominator, you start with R1, R2.
So this one has integral over R3, R4, R5, right?
Yes.
And this one had integral over R1, R2, R3, R4, R5. So that disappeared. When you differentiate it, there is no dependence on R1. When you integrate it, the dependence on R1 goes away. The top one still has a dependence on R1. So this term simply does not matter. This term does not matter. That's why it's the same.
Your nabla was with respect to the difference in the two distance.
R2 still hangs. R2 is like, I'm gonna stay here. I'm just don't like ignore me. I'm here, you know. Yeah, go ahead.
It was the left-hand side of the expression was V of R, where R was the vector difference between R1 and R2.
And here.
No, 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 no. In this, okay, so when I started doing this derivation, I'm not looking at differentiation with respect to R. I'm actually differentiating with respect to R1, the vector. That's why it's a gradient. So I'm trying to find middle ground between what Chandler does, which is extremely general, and what we are really caring about, just radial thing. We'll come to radial thing in a moment. Okay, so R2 is still there. The same idea swimming that we had earlier, that when you differentiate a function of x, y, z with respect to x, y and z do not disappear. In this case, for one will stay because, well, it stays, you're not integrating it out. 2 will stay, even though you did not differentiate with respect to 2, it's going to stay because you're not integrating out 2. Okay, that's why it's going to stay. So let me write down this in this equation on the next page. So we have just shown that minus gradient, and to be very clear, I'm differentiating, it's a gradient. Okay, so what's the definition of a gradient? Partial f by partial x along, gradient is a vector. Remember, if you remember your multivariable calculus, gradient is partial f by partial x along unit vector x plus partial f by partial y along unit vector. So this thing is really partial by partial x along unit vector x1 plus partial by partial y, partial y1 along unit vector y1 plus partial by partial z1 along unit vector z1. That's what we are talking about. That's a gradient. So gradient of here we had gradient of W2, which depends on R1 and R2. Let me write it down in a more general sense. That turned out to be equal to integral of e to the power minus beta u of Rn, the full many body potential. In the denominator, we have the same thing that first shows up, Rn multiplied by dr3, dr4, drn. These are all vectors as of now. This is also a vector. And here the differentiation, the derivatives, well, the variables that you are integrating over are the same, dr3, dr4. The only term that is different is this. There is an extra term over here, which is derivative with respect to R1 of the full many body potential. This complicated integral is nothing but the ensemble average of the derivative with respect to R1 of the full many body potential, but it's a special type of ensemble average. It is averaged over all particles in the set 3, 4, 5 till n. Make sense? So it's a very special type of integral. Okay, this is the first time we have seen it's like a restricted partition function. Now that's what we are doing here. We are keeping R1, R2, we are integrating everything out. So it's an ensemble average. So what have we shown here now is that, and so anytime you have the derivative of a potential, that's a force, right? That's how we get forces. So what is this? This is the force experienced by particle number 1 averaging over I won't write anything else. So force experienced by particle number 1 averaging over particle 3, 4, 5, dot, dot, dot. So what have we just shown? We have said that the force experienced by particle number 1 experienced by averaging over 3, 4, 5 is equal to minus gradient with respect to R1 of W to R1, R2. If I wanted to write down the same force for particle number 2, what would it look like? Minus gradient R2 of W2 of R1, R2. Now we can go to the systems that we are really interested in. In your homework or exam problems, I will never talk about any other system. I will only talk about simple systems where only radial things matter. If I am now interested in the force as a function of the distance small r, so this is modulus of R1 minus R2 between particles 1 and 2, what is that going to be? Anyone? Can we get that from this? Can we just write down gradient with respect to the distance r? Or can we not? We have to be careful. Okay, this is the last thing we have to do today. We have a few minutes left. So let me write it down again. So we are saying that force experienced by particle 1 when you are averaging out particles 3, 4, 5, ... is minus gradient with respect to the position of the particle 1 of W2 of R1, R2. And if at this point you're like, wait, where did W come from? Just to remind you, W was log of G, right? W is just radial distribution function with a -1 over beta on a log scale. So so on left hand side, we have a force, but this is a very special type of force, right? If you observed two particles at a certain time and they had a certain distance r, is this the force that they are experiencing at that point of time? No. What is this force then? It is really averaging, really invoking the ergodic limit, right? If you observe everything else. So in experiments, this is quite simple, right? If you run an experiment, you tag two particles and you study the force between them, and you run your experiment long enough, this is going to be the average force that they experience, right? So it's a mean force, right? It's not an instantaneous force, it's a mean force. And you got this mean force by differentiating something. When you differentiate, what is it that you have to differentiate in? What is the quantity in physics that you differentiate to get a force? It's a potential energy, right? So this thing, therefore, is called potential of mean force. Okay, because by differentiating it, you can get your mean force. And again, it's a very special type of force. If you have two particles, it means that the force between them as a function of r is coming from averaging out everything else wherever else they can be. It's almost like a, it's like one of those time-lapse movies where you're focused on only two particles and everything else in the background is like very fast and sped up. You know what I mean? Maybe it does not help. It's like, whoa, what's going on, right? I'm saying that. So it's a very special force. It's a mean force. Mean, not in the sense of it's mean, horrible force. It's a thermodynamic average, okay? It's a thermodynamic average calculated using this. Now, the final expression that I want to write today, and I want you to think about it, is that if you have simple, well, I shouldn't call it simple. If you had isotropic systems with only radial interactions, then you could say that the force between two particles, the mean force between two particles as a function of their distance r would be minus d by dr of w of r. Okay, that's the key idea over here. And now we can write down, so what is w? So w is, yeah, I don't think we need to write down anything. Okay, good. So we covered very new material today. The homework 5 will be basically manipulating these ideas. So you get intuition for all these things. Okay, like calculate g of r for something, calculate force, use this just to, so you develop familiarity with all of this. Any questions? So this is all done in Chandler's chapter 7. He does it for a more general setup. And I really like this part because this is really StatMech for chemistry. Many of the topics that we have done in the course thus far, if you have had, especially an undergraduate degree in physics, you have probably seen it. But this type of material is very new. This is fundamental to chemistry StatMech, and it's really, really powerful. Okay, good. So see you next time.